Right. Okay. I'll just choose the right mouse cursor. So the first one, that's just like an overview. So let's see, the energy topic is split into these three sections. So the first section is just called energy changes in a system and ways it is stored before and after such changes. That's a bit of a mouthful. Essentially, what it's saying is it's talking about energy transfers. So we know that when there are many different types of energy, we'll learn about that in Key Stage 3. And we also learn in Key Stage 3 how an energy can change from one form into another. So what we go on to do at GCSE is learn about how what sort of calculations can be done there. Okay, so for example, you could use if you knew a ball was falling. I'll just draw a brief example. Let's imagine we had this ball here, and it was falling. Whoops. So I'll draw an arrow going down. If we knew how high it was going to fall, whoops. Sorry. If you knew how high it was going to fall, which is so h is equal to, for example, 5 meters, and if we knew the mass was like 2 kilograms, then we know what planet we're on, like Earth, for example, then on Earth, the strength of gravity or the gravitational field strength is 9.81 newtons per kilogram. Then we'd be able to work out the gravitational potential energy, mgh. And if we're then trying to work out what is the final velocity just before it hits the ground, how fast is it going to get up to as it falls? Well, we know that in terms of the energy transfer, we're getting gravitational energy is being converted into kinetic energy. So there is going to be some thermal energy as well. But if there was no thermal energy, then we could say that the gravitational energy would be turned into kinetic energy. And then you could rearrange the formula for kinetic energy. That's elastic energy. Kinetic energy is the one above, I believe. You could rearrange the formula for kinetic energy and calculate what its final velocity would be. Or let's say that they've given you the various values so you can work out the gravitational energy and you can work out the thermal energy. You can work out the gravitational energy and you can work out the kinetic energy. They may ask you how much energy was converted into heat, and you would subtract the gravitational energy. You would subtract the kinetic energy from the gravitational energy. So at GCSE, it's really all about manipulating these ideas of different energy transfers. Now, another thing that comes up within this within this section is heat transfers, energy transfers of heat, and that is, and most specifically is specific heat capacity. So there was some quite good animations on different areas of my database that I've just added recently, which we can look at in a moment. But what is specific capacity in general? It's how much energy is required to heat a kilogram of something by 1 degree C. So if you heated up, if you gave one object, let's imagine we got these two objects here. We've got one object here, which let's call that object A, and then we've got another object here. Let's call this object B. Let's make object B a bit bigger. If I gave both of these 100 joules of energy, clearly object A would get hotter than object B because if they're the same material, object A would get hotter than object B because object A is smaller, and so it's going to be easier to heat it up. So when I give it 100 joules of energy, it's going to get hotter more quickly with the same amount of energy. Now, sometimes even if it's the same same size, same mass, like this now, it might still not be the same amount of energy to heat it up to the same temperature change, because they might have different specific heat capacities. In other words, it might be easier to heat up one than the other, and also you could therefore think about within each degree centigrade, a larger or smaller amount of energy is contained in that, and the amount of energy that was needed to heat it up by that amount can be calculated using this formula. So it's going to be the mass multiplied by the C, which is the specific heat capacity of that material, multiplied by the change in temperature. So that's what specific capacity is. That's basically what we need to know. There is some more complicated stuff about specific latent heat, which comes into it as well. I presume it's in this topic as well, although I don't see anything. It's definitely in the exam specification. I don't see anything there. It might come up in the different unit instead. But so let's go on. The next bit is all about power. So now, and let's talk about work as well, although they've not talked about it here. What is power and work? Well, first, work. Work is when you are converting one type of energy into another, then you're doing work. Or you're converting one type of energy into another deliberately, then you're doing work. So let's say we have a motor is converting electrical energy into kinetic energy. Then the amount of kinetic energy it's produced is the amount of work it's done. Work is also the amount of energy that was used. Here you go. Should I tell you here? Does it tell you? Okay, it doesn't give you a definition of work, but it's the amount of energy that's been converted usefully. So it might the electric energy might have also been converted into thermal energy, but it's this energy, the useful energy, which is the work. That's the amount of work that was done. So how powerful is something? Something is powerful if the more powerful something is, the more quickly it's able to do work. So, or we could say the more quickly it's able to convert energy. So the power is going to be equal to the energy converted. So it could be kinetic energy over time, or it could be the work over time. Okay, that's what power is. And this little equation here, this energy transfer diagram here that I've done, could also be thought of as being a Sankey diagram. You could show this information using a Sankey diagram to show how much energy was useful and how much was not useful. And it would be drawn like this. You've probably seen these Sankey diagrams. It should be that the width of this arrow here plus the width of this arrow here should be equal to the width of this arrow here. And so if that was 5 centimeters and this was 2 centimeters, this would have to be 3 centimeters. And then you'd have a scale that would represent the amount of energy. So that could be 20 joules, that could be 30 joules, and that would have to be 50 joules then. The arrow pointing to the right is always the useful one. And the arrow pointed down, or sometimes up, is the wasted one. Sometimes you have more than one useful, more than one wasted, and then the diagrams get more complicated, but essentially that's the general rule. All right, so there's Sankey diagrams. You can also look at how efficient something is by calculating by doing a ratio of how much useful energy was transferred divided by the amount of energy that was put in. So total in. Okay, so that's the first. That's the first third. It probably is more than a third, to be honest. As you can see, it's got more pages, but that's the first of three sections in a nutshell. All right. So I'll stop the video there, and we'll see if we can have a look at the next video, next section.